In this recording, we're going to look at the locus definition of a parabola. So you've looked at some other forms of a parabola in Algebra 1, but we're going to look at a unique way here that actually is useful for modeling. And the definition here is similar to what it is for the circle. You remember for a circle, you have a locus definition that says it's all the points that are equidistant, meaning the same distance from a certain point. That makes sense. Parabolas are slightly more complicated. They have two places that all points are equidistant from. Okay, so a parabola is the collection of all points equidistant from a fixed point, and we call that the focus, and a fixed line, which we're going to refer to as the directrix. Okay. So let's consider the application of such a definition. You've seen satellite dishes before. Well, it turns out a satellite dish is a parabolic curve. So basically it's a parabola rotated around to create a 3D shape. There's this receiver in the middle, which you could refer to as the focus. And using this diagram, you can see that any point on the parabola would be the same distance, or it's equidistant from this focus, this receiver. So as a satellite beam comes in here, it's reflected off the arc, the parabolic curve, and received by this focus, this center. Let's look at another vision here. This is a blue parabola, a green point, which is called the focus, and a green line, which is called the directrix. You can see that any point, I'll move this purple point along the curve, and you can see down here at the bottom how L1 and L2 stay the same. Okay, excuse me, they don't stay the same, but they stay equal, I should say. They are equidistant. Any point is equidistant from those 2 points. Now I can move that focus. Notice how the directrix moved as well. There's still 2 units from the vertex to the focus and 2 units from the vertex to the line. That's easy. But also as I move along the curve, it's the same distance from the curve to the line and from that point on the curve to the focus. So let's do some problems that involve this. First scenario here gives us a parabola already, and it gives us the function. Okay, so it says this is the function y equals 1/4 x squared plus 1. It gives us the focus, and you can see that it's at the point 0, 2. You can see the directrix is the x-axis, as it says. And our task, first off, just underline those 2 facts. Focus is at 0, 2. Directrix is the x-axis, which we could refer to as the line y equals 0. So it wants to know, okay, and this is going to be a simple just counting question. How far is the turning point, or vertex, 0, 1, from both the focus and the directrix? So let's just do a counting here. So from this point here, this 0, 1, it's 1 unit up to the focus, 1 unit down to the directrix. So from right here, we would say 1 unit. And then from the point 2, 2, well, you can see it's 2 units straight down, 2 units straight left to the focus. So that point is 2 units. Well, let's take some other points. We're going to look at the point 4, 5. Okay, for 5, we're going to need to draw some segments. Okay, so it suggests drawing a segment from the focus to that point 4, 5. You can see that kind of makes a little triangle here. I'm going to use the Pythagorean theorem or the distance formula to determine that distance. And we also have the distance here from the point to the directrix. So that's just easy counting. We can count 1, 2, 3, 4, 5. We can see that that's 5 units. So we know, we call that D1 maybe. D1 equals 5 units. And we have to find out D2. D2 would be this diagonal distance, and I'm going to use the distance formula for that. So let's just recap what the distance formula is real quick. I'll just write it up here. D is the square root of x2 minus x1 squared plus y2 minus y1 squared. And where this comes from is your Pythagorean theorem, right? You have this triangle right in here where this is the difference of the y's. That's y2 minus y1. That gives me the vertical distance. That's right here. This is the horizontal distance, the distance between the two x's, x2 minus x1. And when you square those and add them up, you get the hypotenuse squared, right? And then you could square root it to get just the hypotenuse, or the d. So it just comes from your Pythagorean theorem. So d2, in this case, let's keep it with the blue pen, d2 is the square root of 4 minus 0 squared. I'm subtracting my x's. 4 minus 0. Could label that point, that focus. And plus y2 minus y1. So 5 minus 2. I just have to do out the math there, just evaluate that. So I've got 16, 9, add those together is 25. So the square root of 25 is 5, which checks. Okay, we wanted to show that those distances were the same. Now it says do that same work for the point 6 to 10. Well, let's grab our red pen and let's make a segment that's vertical here. So I know that's going to be 10, right? Because the point is at 6, 10. So I know that distance is 10. Call that D1. And then my horizontal distance, again, I'm going to need to use the Pythagorean, or the diagonal distance. I'm going to use the Pythagorean theorem or the distance formula to work this out. So why don't you work that out, play the recording when you've got it. Okay, so hopefully you worked that out. You got your distance formula, and I'll just work this out quickly and you can see it. We could continue to take individual points and find their distances and confirm that their distances are equal. But maybe we could be a little more efficient by, in fact, looking at any point, kind of making it general to any point xy. And that's what it says at the bottom here. Use the distance formula to show that any point on the equation will have this relationship based on the definition. So let's work that out. So I'm going to imagine a distance from the focus. Let's just jot that down. The focus, so the distance from the focus, 0, 2, and I'm going to call this x1, y1. All right. Now, if I want to find the distance here, it would be d equals, now I'm finding it between the distance from the focus to any point. So that other point is just called x, right? So I'm going to go x minus 0, I'm using this as my other point, squared, plus y, some generic point y, minus 2, squared. Okay, now I just need to do out this math here. All right, we can do that in a second. On the other hand, I've got the distance from the directrix. Y equals 0. So the distance from the directrix to any point will just be its y value. So it'll be d equals the y value of that point. So then what I want to do is set this expression equal to that expression and do out the math. Okay, so I'm just kind of bring this together with that. Set the two d's equal. So I've got y equals, then this expression. Now I just need to square both sides, get rid of the square root. So I've got y squared on the left side, and on the right side, x minus 0, can I just say that's x, right? X squared. And then when I work this out, if I evaluate this out, I'm going to get y, don't need that extra paren there. It's going to be y squared minus 4y plus 4. You could expand that all out. Now the good news is, hey, there's y squareds on both sides. So those just add to 0. I can bring my y over to the left side by adding 4y. And now I've got x squared plus 4. To get y by itself, just divide. I end up with y equals 1/4 x squared plus 1. And that's the equation of the parabola that we were looking to demonstrate. Thanks for watching.